Hello, can you hear me well? Can you hear me now? Okay. All right. Let me just, okay, should be recording. Should all be fine. Right, yeah, it should be all right. Okay, great. So, did you have a chance to look at the problems from the assignment 5? We apologize that it's not published yet, but you can access the problems. Jasmine, Judah? I have briefly. Good. Did you find anything interesting, unusual, something that you had mocks? Okay. All right, that's fine. And Judah, what about you? No. Okay, that's fine. Oh. Can't see anyone. Oh, okay. Right, yeah, that makes sense. Spotlight. Okay. Well, I've chosen, what about Kieran? Kieran, did you have a chance to look through the problems from the assignment 5? Not yet. Okay. So, but you know where to find them, I hope. There's a link. I've posted the link. This is the link to the whiteboard, which I'm using for the webinars. So yeah. So let's get to it. So a few things that I've chosen a couple of problems to do today, which I find interesting or just necessary to understand the topics. So don't worry if you haven't done all the topics yet, but you should, by my understanding, you should be familiar with most of the topics, because in 1 or 2 months you'll just start preparing for your exams, and that's about it. Okay, a rocket of mass 2 times 10 to the 3 kilograms is fired vertically upwards with a constant acceleration. After 1 minute, it reaches a height of 36 kilometers and its engine is switched off. Assuming the rocket mass and the value of g remain constant, calculate the initial acceleration of the rocket. Okay. So how would we do that? Feel free to shout out. Feel free to write things in the chat. How would you work that out?
When you say the initial acceleration, do you mean before the engine switched off, when it actually starts?
Yeah, when the rocket is fired.
Would you use suvat because it's constant acceleration?
You would use suvat, yes. So I mean, the first thing that comes into mind is F equals ma, but since we don't have F, that's quite a bit of useless thing to do. So yeah, suvat, of course, suvat. So the first is suvat. We say the acceleration is, well, the mass is constant and constant acceleration, of course. So you can use suvat. So S is 36,000. U is 0. Yeah. So V is, well, we don't know and we don't really care. Acceleration is what we are looking for, and T is 1 minute, so 60 seconds. 60 seconds. So we choose a formula without V, and that is, of course, S equals UT plus a half AT squared. So S is 36,000 equals a half times A times 60 squared. Ooh, interesting. 60 squared is 3,600 and 36,000. So we're left with 10. So A is 20 meters per second squared. Okay. That's 20 meters per second squared. The maximum height reached, well, okay. A student, a not so sophisticated student would say, well, the maximum height is 36 kilometers, isn't it? Because it reaches 36 kilometers and the engine switches off. So that is the maximum height, isn't it? What would you say to that student? Keeps going up. Absolutely. I mean, it doesn't at if it's traveling 1 minute at 20 with an acceleration of 20 meters per second squared. So 2, so the final speed, final velocity is acceleration times time, which is 20 times 60, which is 1200 meters per second. That's the final velocity before it starts to decelerate. And then we need to use a suvat. So because it reaches, it's at 36 kilometers, and it's traveling upwards at a speed of 1200 meters per second. So it will travel up at some point and then it will start falling down. So we need that H. So we use suvat. S is H, is what we're looking for. U is 1200. What is V?
0.
0. Well done. And acceleration?
Minus G.
Minus 10. Yes, very good. And T is, well, we don't really care. So we use the formula for suvat without T. That is V squared equals U squared plus 2AS. So 0 squared equals 1200 squared plus 2 times minus 10 times S. So S is 1200 squared divided by 20. Right, that's going to be, that's 1200 times 20 times 60. Yeah, 20 times 60 is 1200. Yes, divided by 20. So that's going to be 20 times 3600 equals 72,000 meters. So the total height is 108 kilometers. So maximum height. Yes, it is the assignment. We are going through the actual problems from the assignment. So this is the assignment. You can see it. Okay. This is the draft. It will be published this week. Draft. And it's not due the 22nd of January, of course. It is due on the 29th of January. Okay, moving on. So maximum height is 36 kilometers plus 72 kilometers. That is 108 kilometers. Okay. Maximum height reached is 108 kilometers. The total time of flight. Well, we'll need to find out how long it will take to fall down. So it took a minute. Well, there are like 1,700 ways of doing this question. Problem 3. We know that this thing took 60 seconds. So this is here, t is 0. Here, t is 60. And then we can say, well, we can find the time to reach the maximum height, and then find the time to fall down. But this is pointless. You do not want to do that, because then you have to do 2 separate calculations. Yeah, do it in one step. So it's a SUAT. You really need to realize that you're starting from here, you're going here, and you end up here. So SUAT. But this SUAT is tricky. So what is S? S is the trickiest bit.
Is it minus 3,600 meters?
36,000. Yes, well done. Absolutely. Because S is the displacement from here to here. This is minus 36,000. Does everyone understand that? Please type in the chat. The initial velocity is 1,200. Final velocities we don't know and we don't really care. Acceleration is minus 10. And time is the question mark. So we take the formula without v. So S is equal to ut plus a half at squared. And S is minus 3,600, 36,000, sorry, equals 1,200 t minus 5t squared. Okay, t squared minus 1,200 divided by 5. So that's divided by 5 is the same as multiplied by 10 divided by 2. So 12,000 divided by 2, 6,000. What? That doesn't make any sense. Divide by 5 is multiplied by 2 divided by 10. So it's multiplied by by 2, which is 2400 divided by 10, 240. 40 t minus 36,000 divided by 5. So once again, multiplied by 2, divided by 10, 7,200 equals 0. So t minus t plus equals 0. Let's see, two numbers multiply to make 7,200. I'm guessing is going to be 120 and 2. 120 and 2 is not possible. 20 and 12. 20 and 12. 20. No, not 7,200 divided by 20. No. Okay. Oh, okay. So it doesn't really factorize. Really, I thought I had it. Anyways, so either T1 is 267 seconds, and T2 is minus 27.0 seconds. 27.0 seconds. Now, of course, T cannot be negative. That's obvious. So the answer is 267 seconds to reach plus 60. So the answer is total time. Total time is 267 plus 60 is 327 seconds. Okay, so we have this. 327 seconds. However, T2 is not a random number. What is T2? Can somebody use the microphone to explain what is the meaning of minus 27 seconds?
Is that just if it was the other way around? So like it would be at the same place, but minus 27 seconds ago if the acceleration had stayed the same.
Exactly. If the motion had stayed the same, if the acceleration had stayed the same, it would have traveled from here. So this is t equals 0. This is t equals something, but this would be t equals minus 27. And then it goes up, and then it's this, and then t is 267 seconds. So this is where it was, where it would have been 27 seconds ago if it was the same acceleration all the way through it, which it wasn't. The work done by the rocket. Well, it's not a good question. What do we mean by the work done by the rocket? By the rocket's engine, perhaps? Yeah, the rocket's engine, and assuming 100% efficiency, because it's so this question is honestly so bad. So I will have to edit that. The useful work, or the rocket done by the useful work done by the engine of the rocket. You have to be very precise what you mean here. Sorry, I'll just edit the thing. Useful by the rocket, the engine. Okay, I've changed that. Now, somebody suggested the kinetic energy and potential energy. Yes, that is true. The work energy principle says that the change in kinetic energy plus the change in potential energy is the work done. But I mean, we don't really need for the we can look at the top point. At the top point, the kinetic energy is 0, and the potential energy can be easily calculated, mgh. So the work is equal to mgh at the highest point. So its mass is 2 times 10 to the 3 times g10 times h, which is 108,000, which gives you something huge. So 2,000 times 10 times 108,000. 2.16 times 10 to the 9 joules. Right. Okay. To the 9 joules. Explain why the assumptions in these questions are unrealistic. Okay, can somebody tell why are the assumptions unrealistic? Drag proportional to velocity squared. Velocity squared and high velocity is reached, so you can't say it's negligible. Exactly. At 1200 meters per second, you cannot ignore drag. Ignore drag. Although, do they actually say, well, yes, so you cannot ignore drag at this stage, yeah? Here, you cannot ignore drag, but it doesn't say that they are ignoring drag, so yeah. What else? Why else the assumptions are unrealistic? Imagine the same thing, but there was on a planet identical to the Earth, but no atmosphere. And the assumptions would still be invalid. So why would that be? The same assumptions on a planet with no atmosphere would still be invalid. Why? Can somebody tell me? The rocket is losing mass. Well done. Mass is changing. And if you remember the Tsiolkovsky equation, the rocket science equation, mass is changing always. So the acceleration because the acceleration is force divided by mass. Provided the force is constant and the mass is decreasing, acceleration would be increasing. And what else? Yeah, the work done by the engine, like the gases would also have lots of kinetic energy. So when we say work done by the engines, what does that mean? Yeah, so probably I'm saying that they meant useful work. That's the thing. Okay. An object travels with speed v around a circular path of radius r. The diagram shows two positions A and B on the path. Derive an expression for the acceleration. Okay, so this is a very typical thing to do. Acceleration is a vector, and it's equal to the change in velocity, which is also a vector, divided by change in time. So we have v, and we have v. Let's call it v1 and call it v2. Okay. I'm going to move them here. I'm going to move them here. This is v2, which is a vector. And this vector is v2 minus v1, which is delta v. Now this angle is theta, and we can use the cosine rule. Delta v squared is equal to v1 squared plus v2 squared minus 2 times v1 times v2 times cosine theta. And we have delta v squared equals 2v squared, because v1 and v2 are the same thing, minus 2v squared cosine theta. So delta v is equal to square root of 2 v square root 1 minus cos theta, sorry. There's no square. 1 minus cos theta. Okay. Are you still on board? Is there anything you didn't catch here? Still on board? Judah, Kieran?
We're on board.
Yes, good. And Kieran? Yes. Okay. So we need to find, we are looking for this vector, this little red vector, which is the change in velocity, We used a vector diagram to find that this is the change in velocity. It's this. Then we use the cosine rule to find this length. And now we use the small angle approximation. Small angle theta. Therefore, cos theta is 1 minus theta squared over 2. And you can plug that in. Root 1. Well, no, because if it was cosine squared, but it's not. If it was cosine squared, then yes. Oh, we have more people. Hi, Hannah. Say square root of 2 v 1 minus 1 plus theta squared over 2. 1 cancels, 2 cancels, and we're left with v theta, which is beautiful. Approximately, of course. So delta v is approximately v theta. Okay, so we'll write this down here. V theta divided by delta t. So what do we know about delta t? Well, we're traveling at velocity v, and if we cover this angle theta, we need to find the length of the arc. So the length of the arc, or just I would say delta s, delta s arc, delta s is equal to v times t. So t is equal to delta s divided by v. But we know v delta t, sorry, delta t. So delta t is delta s over v. But we know that the arc is r theta, because you very well know the formulas of the length of an arc divided by v. And we can plug that in. So we got r theta divided by v. So v goes on top. So v squared theta. Okay. Theta cancels and we get v squared over r. Now, this is a very important derivation. I urge you to go through it. There's another version where you go from, and it's covered in one of the assignments, by the way. It's covered in one of the assignments. So you start with the circle, and you have velocity here, and then you do so this is theta, this is theta, and this is v, and then you find the difference. And because in this case the difference would be like this, so it's v like this and v like this, you can see that the change delta v is exactly vertically down. Okay, and then you don't have to use the small angle approximation formulas. It will work. Or do you? Actually I forgot. Okay, well, leave that. It is covered in assignment 1. Okay, so refer to that if you forgot. Okay, so the answer is that the acceleration is v squared over r, or alpha is equal to v squared over r. Jasmine, no, I don't teach first year modules. I mean, the photographs show a toy with small no, I only do COMPOS at Oxford. That's my full-time job. I do tutorials sometimes for small groups for undergrads, but that's a one-off thing when they ask me to do it, but not on a not regularly. The photographs show a toy with small airplanes suspended from a canopy by wires. As the canopy rotates, the airplanes rise and follow a circular path. At a particular speeds, the airplanes follow a circular path of diameter 10.8, and the wires make an angle of 19 degrees to the vertical. Okay. Complete a free body diagram for one of the airplanes at this speed. Well, this is quite straightforward. You have the gravitational force, you have the tension, and that's it. So this is mg. Gonna make it smaller. Okay, mg. This is tension, and this is the angle theta. So write down Newton's second law. Newton's second law. So vertically, this is T. So T cos theta is equal to mg. Horizontally, it is accelerating horizontally because it is unbalanced. The forces, horizontal forces, are unbalanced. So horizontally, mass times acceleration is equal to T sine theta. Okay, is this clear to everyone? Type something in the chat to let me know. Does this make sense? How many people do we have today? Okay, 5 people. We have Matty as well. Hi Matty. Okay. Okay, show that at this speed, the time for an airplane to make 4 complete rotations is about 3 seconds. Mass of an airplane is 5.2 grams. So we've done the free body diagram. Show that the speed for complete mass of an airplane is 5.2, and we know the angle 19 degrees. Do we know the radius is 10.8? So we take this. This is for question C. This is for question C. We know that acceleration, the acceleration, because it's moving in circles, is v squared over r. So we know that the radius, well, but we're interested in the frequency actually. So we can rewrite this as omega squared r. Okay, and then we know, so r is 5.4 centimeters, as far as I remember. 5.4 centimeters, because the diameter is 10.8. So what else do we know? We know that the mass is 5.2 grams. I don't see how the mass is important here, but let's write it down. And we know that the angle is 19 degrees to the vertical. Okay. So we take this formula. Well, take both these. Well, we take all three formulas actually, and we put one into the other. So mass times omega squared r is equal to T, which is from here, T is mg divided by cos theta. So mg divided by cos theta multiplied by sine theta. So m cancels as predicted. Omega squared is g tan theta divided by r, or for complete rotations is about 3 seconds. We can work out that the time period is 2 pi divided by omega, which is 2 pi square root of r minus g tan theta. Does this look familiar to you? Yeah, t is 2 pi square root of L over G. Oh, here it's just slightly modified version. So it is. And we find that the t is 2 pi divide r, which is 0.054 divided by 9.81 times tan theta, tan 19. So 2 pi multiplied by square root 0.054, 9.81 times 10, 19, 0.794 seconds. And it says in 4 rotations in about 3 seconds. So 4 rotations is 4t, which is 4 times 0.794 is times 4, 3.18 seconds, 3.18 seconds. Cool. That's indeed, the formula for circular motion and the formula for pendulum are almost identical. It's not a coincidence. Student A suggests that if the radius of the canopy was increased and rotated at the same angular velocity as before, the wires supporting the airplanes would be vertical. Student B suggests that the wires would be at an angle of greater than 19 degrees to the vertical. Explain whether either of the students is correct. The radius of the canopy. Okay. Well, yes, they're only vertical when it's stationary, of course. So let's talk about student A. Student A, D. Very well, Jasmine. Yes, by all means, it can't be vertical. Because if it is vertical, it's because it's moving in circles, it has to be accelerating. There are no forces to accelerate it because the only two forces is mg and tension, and there are no horizontal components. Therefore, not possible. Wrong. No horizontal components. Now, student B. So student B says that it will be greater than 19 degrees to the vertical. So what we have here, the radius has increased. So the radius is bigger. Therefore, MA the same angular velocity, O, M omega squared R is going to be M omega squared R is equal to T. Well, we can use G, mg tan theta. Mg tan theta. So M cancels. And because omega stays the same, well, we can say tan theta is equal to omega squared R divided by G. So if the radius increases, G stays constant, omega stays constant, then tan theta increases. That means theta increases. Greater force inverse is required to maintain the same angular velocity. True. Yes, you can say that. You need, the further you are from the center, that means the faster you go. And the faster you go, yeah, if you double, let's say you're on a wheel and you double the distance from the center. You're on a wheel and you were here and now you are here. Now, the centripetal force is m omega squared R. Or you can say F is mv squared over R. So let's look at this formula. The radius increases, so it looks like, if you look at just this formula, if radius increases, it looks like this will decrease. But no, because you go further away from the center, V increases. V also increases, and because V is squared, overall F increases. And here it is very obvious because there is as the radius increases, force increases. If radius increases, the force increases. Okay, so don't allow them to trick you. And if they ask what happens to the centripetal forces if radius increases and they give you this formula, be smart. Okay. Good. Although if velocity is constant, then it's a different story. Okay. Problem 5. An alpha particle with initial kinetic energy of 4.9 MeV is directed towards the center of a gold nucleus of radius r, which contains 79 protons. The alpha particle is brought to rest at a point S, a distance r from the center of the nucleus as shown in the diagram below. Calculate the electrical potential energy of the alpha particle at point S. Well, there's a formula for that, of course, but let's do it properly. Okay, not like this. Let's remember the definition. Potential energy, work required to move a charge from infinity to a given point. So we're moving the alpha particle from infinity to the given point, to point S. Now, what is the work? Let's say the alpha particle moves a small distance. The alpha particles moves a small distance, d, well, delta. Now let's call it dr. Okay. The force required is F. The force, because there's a repulsion between the gold nucleus. Gold nucleus is positive, and the alpha particle is positive. A force is required to do that. A force is needed. So work, the small amount of work, dW, is equal to the force times dr. Force times distance, right? Because we need to move the alpha particle, we have to push it. And the small amount of work, if the alpha particle is moved dr by force F, work dW is FDR. Okay. Now we know the force. The force is equal to Q1 Q2 times K divided by, well, not K, 4 pi epsilon 0. One divided by 4 pi epsilon 0. That's K divided by R squared. R squared and dr. Okay, so these are all constant. So it's equal to Q1, Q2 divided by 4 pi epsilon 0 multiplied by 1 over r squared dr. Or in other words, r to the power minus 2. Power minus 2. And now we integrate. We integrate both sides. Integrate both sides. So integral of dW is equal to the integral of, well, because this is a constant. Oh, okay, I'll write it down like this. And integral of this, but because this is a constant, the integral just goes here. Okay. Now we need the limits. You can do it with a constants, with a C, but I prefer limits. So the work, when you start, you have done 0 work. When you finish your job, you have done W work, W amount of work. When you start R is infinity. And when you finish, R is R. Now, this is not a very good way of writing, because how can the limit contain the same variable as here? But what we mean is this is a fixed value. R is the final value, R whatever. Yes. Sometimes this is acceptable, although, for example, Professor Lvovsky really hates it when you do it like this. So it's very individual. I find it perfectly acceptable when you have the same variable, but technically it is wrong. Okay. But you will sometimes see people do that. For example, the integral from 0 to t of t squared dt. Yeah, so a lot of mathematicians and physicists would say, no, you can't do that. But anyways, I'm going to say, so Q1, Q2, 4 pi epsilon 0. And then the integral of r to the power -2. Quickly, somebody shout out. I've been talking way too long. Come on.
Minus r to the -1.
Minus r to the -1. Yes, there's no 2 here. Yeah, so don't, there's -1 over r. Okay. And we go from infinity to r. So it is Q1, Q2, 4 pi epsilon 0. -1 over r plus 1 over infinity, which is 0. Which is 0. Therefore, it is minus Q1, Q2 over 4 pi epsilon 0 r. Yet again, you can't really write 1 over infinity. You have to do it like this. You have to say it's the limit as delta, delta is the limit as delta tends to infinity of Q1, Q2, 4 pi epsilon 0 of -1 over r plus 1 over delta. Okay, so what does it say here? It's delta tends to infinity, -1 over r plus 1 over delta. So technically, what I've written here is just a short way of writing this. Okay, so just be careful. You cannot actually divide by infinity, because infinity is not a number. You can't divide by it. So when I say this, I actually mean 1 over delta, where limit of delta to infinity. Okay, so I hope that makes sense. All right, so yeah, and that's the work done. And here the left-hand side integral is just W, because it's W minus O. So that is minus Q1 Q2 over 4 pi epsilon 0 R. Now, what is Jasmine? You are writing direct messages, so nobody can see it, just in case.
Sorry,
I'd
just
prefer-
using an integral.
As opposed to what? As opposed to?
I mean, usually you wouldn't, like, we've sort of derived it, but usually in school we'd just say, like, we'd just take the equation for potential energy,
Okay.
and it's just not as nice. It doesn't give you an understanding.
Oh yes. True. And the expression for the potential energy is Q1. So K Q1 Q2 4 pi epsilon 0 R. Now the only thing is, like, why is there a minus here? Because potential energy is clearly positive here, because you're putting a positive value.
I don't know if this answers the question, but is it because work is equal to the change in kinetic energy, and kinetic energy decreases, so when we make them equal, the negative signs are going to cancel out?
You have kinetic energy, and you lose kinetic energy, it becomes potential. So potential has to be positive. Or are you talking about that the work done is the work done on the particle is negative? Oh, the work done by the field is negative, of course. Just a second, I'm trying to make sense of it. Yes, the work done by the field as it moves, not by you, is the work done by the field. Work done by field to move a charge from infinity to a given point. And so the field has an opposite force. The field has a force to the right, and this force is going to be negative because, well, no, the work is going to be negative because the force is in the opposite direction of dr. So work is force times dr times the cosine of the angle. So cosine 180 degrees times cosine 180, and that makes it negative. Because it's negative, 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 negative. And then it becomes positive. Positive. Okay. Okay, Q1. Does that make sense? Potential energy next to a positive charge has to be positive, because if you release it, it becomes kinetic energy. And at infinity, you will have not 0, but you will have kinetic energy. Okay. Yes. So the work is KQ1, Q2. And yeah, so you just do that. So it's K. Well, 4 pi. So 1, so 79 times 4, 79 times 4 times. So 79 times 4 times 1.6 times 10 to the minus 19 squared divided by 4. Oh, sorry, there's no 4 pi epsilon here. It's just R. So 4 times 3.14 times epsilon 0, which is 8.85 times 10 to the minus 12. Double check that it is true. 32 constant 32. 8.85 times 10 to the minus 12. Yeah, perfect. So we have 79 times 4 times e squared. Ninety-nine times 4 times 1.6 squared divided by 4 divided by 3.14 divided by 8.85. So 727 times 728 times 10 minus 38 plus 12 minus 26 joules. Calculate R, the distance of the closest approach of the alpha particle of the nucleus. So here we have a conversion from kinetic energy. So kinetic energy turns into potential energy. So half mv squared at the beginning is equal to the potential energy, 7.28 times 10 to the minus 26. That doesn't make any sense. Oh. Oh, sorry. What am I doing? No. You have a conversion from kinetic energy to potential energy. Therefore, as the kinetic energy decreases, as you approach S, the potential energy increases. So the potential energy at point S is simply 4.9 mega electron volts. Calculate R, the distance of the closest approach. So yes, we have a conversion from kinetic energy to potential energy. Therefore, 1/2 mv squared is equal to Q1 Q2 divided by 4 pi epsilon 0 R. And from here, R can be found as Q1 Q2 divided by 4 pi epsilon 0 mv squared. Oh, we have the kinetic energy, sorry. We're not given the mass, so the kinetic energy. So it's just the kinetic energy. Okay, so that's 79 times 4 times E squared divided by 4 pi epsilon 0 multiplied by 4.9 mega electron volts. So that's 4.9 times 10 to the 6 times E. E, which is the charge of the electron, because an electron volt is 1 electron volt is 1.6 times 10 to the minus 19 joules. So here these cancel out. You had 79 times 4. So 79 times 4 times 1.6 times 10 to the minus 19 divided by 4 pi times 32 times epsilon 0 times 4.9 times 10 to the 6. So 9.27 times 10 to the minus 14 meters. Okay, that's a really close approach. This is the size of a nucleus. Determine the number of the nucleons in the gold nucleus are the radius of the gold. Determine the number of nucleons in the gold nucleus. The radius of the nucleus is 7.6 times 10 to the minus 15. One more thing. Determine the number of, so yes. Okay. The radius of the atomic nucleus is given by the formula R0 multiplied by the atomic mass to the power 1/3. Okay. And we know that gold is 198, the mass atomic number for gold. Gold is 197. So it's R0, which is 1.23 times 10 to the minus 15 multiplied by 197 to the power 1/3. So it's a very straightforward question. Just need to remember or have the formula at hand. 1.23. I wonder if I have this constant. I should. No, not really. Well, anyways, 1.23 times 10 to the minus 15 times 190 times the cube root of 197. 7.16 times 10 to the minus 15. Oh, sorry, it's the other way around. Okay, brain function. What I did, I looked up the number of nucleons and I worked out the radius of the gon. We needed to do it the other way around. Anyways, it should be 190, 97. Oh, thank you. Thank you, Justin. Yes. We are trying to figure A out. I got carried away. I was carried away because of the X's. I really didn't like those. And okay, the target nucleus is changed to one that has fewer protons. Well, obviously, if you want A, it's going to be R divided by R0 to the power 3, which is 7.16 divided by 1.23. So you don't need the powers of 10 because they have the same power of 10 and it's a ratio. So it's just that. So 7.16 divided by 1.23 and then cubed. That is 197.25. 97.25. The target nucleus is changed to one that has fewer protons. The alpha particle is given the same kinetic energy. Explain without further calculations any changes that occur to the distance r. Ignore any recoil effects. Okay, so the radius, well, I mean, it depends on how deep they want you to go into that. Okay. Of course, because they are it will come closer. There's fewer protons. So that's the answer to D. Fewer protons means it will come closer. As the force is smaller. Therefore, to do the same work, need a larger distance to do the same work. Yeah, because the work is force times distance. And it's important because there's a force, the electrostatic force. You need a larger distance. The alpha particle needs to travel a larger distance to stop. Therefore, R will be smaller. R will be smaller. That's important. What else? Another thing, well, if they are even smaller, they can go close enough for the strong nuclear force to start acting. If the particle comes close enough, strong nucleus, strong force starts to act. Starts to act. Starts to act. Nuclei might fuse. Might fuse. I have not heard, honestly, I have not heard of a situation where a single alpha particle shot at a nucleus will cause absorption, but I know for sure that alpha particles in the sun, for example, alpha particles do combine together to make heavier elements. So in this case, 4, that would be 8, that would be oxygen. 2 alpha particles combine together to make oxygen. But that's happening in the sun. I don't have the information whether a single alpha particle. Theoretically, yeah, everything's possible. All right, so we have 5 minutes. We don't have enough time to do the later questions. I will do another webinar. Maybe you have any questions I can answer in the remaining 5 minutes. Happy to. Maybe you are preparing for your mocks. By the way, who can you tell me, have you had your winter mock exams yet? Yes or no? Yes, yes. Okay. So I'm guessing those who haven't are preparing, not listening to me on a Thursday night in the process. Okay. Okay, any questions? Any questions that you have? Okay, well, if not, then we can finish for today. Enjoy the rest of your evening. Yeah. Oh, can time take on complex values? I imagined if I'm asking, okay, do you have any questions? And somebody asks, what is the meaning of life? And the answer is 42, of course. But can time take complex values? My first answer would be no, but I don't have but I'm not 100% sure. I'm not 100% sure. I would say most likely the way we define time, it is a real value. But I'm guessing a model is possible where time is complex, but I have never seen anything like that. So I have not met a situation where time is complex. All right. Okay, well, see you next week then. See you next week. Next week we'll probably do physics again, maybe a bit of maths. If you'd like me to go through a particular problem, do send me a message on Slack, and I will. I'm happy to do that. Okay. So just send me a message. Can we go through such and such? All right. See you, everyone. See you next week. Bye.